I'm Jose Antonio Ortiz, and I'm the team lead.
I'm Parrish Ballinger, and I'm working on the error analysis and LabVIEW coding.
My name is Josh Richards, and I'm the design lead for the team.
My name is Bryce Flickner. I'm one of the mechanical engineers.
And I'm Olivia Request, the procurement lead. We would like to thank our sponsors, Dr. Andrew Ryan, Dr. Robert Macke, and Dr. Dante Loretta, as well as our mentor Doug May for their help with this project.
The goal of this project is to create a working gas pycnometer prototype that can eventually be integrated into the NASA Johnson Space Center. This machine measures the volume of rock samples, which can be used along with other measurements to find their density and porosity. The OSIRIS-REx mission was launched in 2016 to gather samples from the asteroid Bennu. When it returns in 2023, the data collection phase will begin, which includes measuring porosity. These data points will then be aggregated together by scientists to draw conclusions about the origin and composition of asteroid Bennu, as well as possibly understand more about the history of the universe itself. Pycnometers are built according to the ideal gas law. Essentially, if the quantities on the right side of the equation are kept the same throughout measurement, then the known volumes and measured pressures can be used to find the sample volume. A basic pycnometer consists of one cell that holds the sample and another that exists as a reference. The first step is to measure the atmospheric pressure using the pressure gauge, because the equations are relative to a vacuum, but this wouldn't be feasible for us, so we must measure the atmospheric pressure and subtract it from our other measured pressure values. The second step is to close the tubing between the cells as well as the exhaust tubing and introduce nitrogen gas into cell 1 to pressurize it. Step 3 is to close the gas input valve and measure the initial pressure using the pressure gauge. This gives us our two initial equations of state, which will be used later to derive our sample volume. A note here is that V1 and V2 include the volume of the attached tubing. The final step is to open the tubing between cell 1 and cell 2, allowing gas to flow between the cells. Then the final pressure is measured by the pressure gauge. This allows us to write the final equation of state and simplify it to solve for the sample volume. Because porosity is a measurement of the empty space in a sample, the porosity is found by dividing the sample volume by the bulk volume, then subtracting this quantity from 1. At the end of measurement, gas is discharged via the exhaust. One of the main requirements of our system is that it shall be able to interface with the glove box at Johnson Space Center. As shown in our system block diagram, only the sample and reference chambers are within the glove box, but the other components must also be built with the glove box interface in mind. Additionally, the sample and reference chambers must only contain Johnson Space Center approved materials. Other requirements are that the system shall use nitrogen gas, cannot destroy the sample, must be able to hold samples with bulk densities in a given range, must be able to withstand 30 psi, and must be able to accept samples from 5 to 25 millimeters in diameter. The thresholds for our accuracy and precision of our porosity are plus or minus 0.015. Finally, the system must be able to be disassembled for cleaning by NASA.
We modeled our system in MATLAB and then used error analysis to find the best design to fit with our sponsor's requirements. In this regard, we looked at the system's accuracy and precision. Accuracy was measured by running 10 simulations on a single sample and comparing the mean porosity measurement to the true value. Precision was measured by comparing each of those simulations to the mean and finding the average of that difference. Ultimately, we wanted both of those to be under 0.015 porosity as per our sponsor's requirement. The main system variable in the error analysis was the reference cell volume. In a pycnometer, the reference cell's volume should match the sample's volume. Unfortunately, this can't be done continuously, and so we had to discretize the change. The final test was with 3 reference cells forming a 1 to x to y ratio. It worked similarly to the 2-cell test, and we found an ideal ratio of 1 to 2 to 4, meaning the smallest cell was 1/7 the sample cell volume, then 2/7 the volume, then 4/7 the volume. This gave us 100% of the points under the maximum desired porosity and almost 100% under the precision. Only the smallest of the samples were affected, and their precision wasn't too far above the desired value, so we decided to use this design and iron out the wrinkles in prototyping.
Many design considerations had to be accounted for in the design of this apparatus. Primarily, material requirements must be met, meaning no lubricants or non-approved metals or plastics could be used. This presented a unique challenge to design a device that was well sealing without the use of those materials. Shearing metal-to-metal contact was also to be avoided in order to mitigate the possibility of particles abrading and potentially contaminating the sample. Finally, the closure needed to be repeatable, meaning the volume of the chamber did not change with opening and closing of the apparatus. The first design iteration utilized a quarter-turn camming latch closure that was very repeatable, but the shearing of the sealing face and the O-ring was deemed a possible point of failure. The second design iteration kept the camming latch closure, but added a sealing piston that was driven by a spring in order to compress the O-ring for a sufficient seal, and to have a repeatable mating face between the bottom of the piston and the top of the sample chamber. The camming latch pins were replaced with screws for improved manufacturability. Ergonomic grip was added to the lid for improved usability, and improved PTFE bushings were added to the points of shearing metal-to-metal contact. The final design was reached after extensive analysis and with care taken to meet the spatial and material requirements of Johnson Space Center. The sample and reference chambers will be mounted onto a stand that will protrude into the glove box environment with pass-throughs for tubing. The controls and pressure sensing will be housed in a sealed box that will be affixed to the outside of the glove box via the glove box interface plate. Each reference chamber can be toggled on or off. This design allows for a number of configuration of the reference chamber volumes in order to achieve the best possible results. The final sample chamber design was a slightly modified version of the second iteration. It still used a spring-driven piston to seal the apparatus, but a cam lever was added to the piston for a number of reasons. With a cam lever, an adequately strong spring could be used in order to fully compress the O-ring. It also allows clearance for the O-ring while the lid is being installed, eliminating all shearing on the O-ring. The reference chamber is a much more simple design. Aside from cleaning and repairs, it does not need to be opened regularly, meaning screws and abraded particles were less of a concern as it will not be serviced in the glove box environment. The dimensions and numbers of the reference chambers were determined analytically as discussed above. The form of the reference chamber was to minimize the footprint of the assembly and to ensure it could be passed through the glove box porthole during assembly.
To summarize this project, our grand challenges included our reference chamber design and our strict materials requirements. Finding a reference chamber that met our accuracy and precision requirements was a challenging task, but we were able to accomplish this through extensive error analysis, which led us to making our 3-chamber design. Contamination was also a major concern, but this risk was mitigated through the procurement and manufacturing process by only using materials approved by the Johnson Space Center. As of right now, we have a manual working pycnometer. This manual pycnometer meets all of our baseline functional requirements. It uses manual valves to operate. As for the future of this project, we would like to integrate solenoid valves and switches into the system. These electronic components provide a contamination risk. Because of this, we will be building a box. This box will house our electronic components. It has already been designed. It just needs to be manufactured and integrated with the solenoids. After that, the system will be complete, and that work would have to be done during the summer.